All right, good news, bad news. Somebody did come out to look at the gas yesterday, but it turns out there's an electrical issue and they couldn't fix it. So somebody else has to come out to look at that. I'm really hoping that we can get this on Friday, but we'll just have to wait and see. So stay tuned for what's going on with the saga with the gas. Okay? All right, with that, as promised, we are going to learn how to describe where every single electron is from any potential atom on the entire periodic table. Yay! So number 51, electron configuration notes. I understand if you'd like to continue on from the page yesterday, just make sure it is clearly marked for your binder quiz. This would be a separate question, separate number for a binder quiz, so make sure that you can keep track of that. All right, here we go. We're actually going to learn two different ways to describe the location of electrons within an atom. And we're going to start with the one that's a little bit more visual and pictorial, if you will. And it's called orbital notation, or I've heard orbital diagrams. And orbital notation or orbital diagrams involves boxes and arrows. So you can see I got a bunch of boxes on the paper here. In orbital notation, we would say that each box that you draw in orbital notation is representing an orbital. Right? So they don't make them the actual shapes, but it could be an S, could be a P, a D, clover leaf, an F, crazy 8 balloon thing. Right? All of those could be the orbitals that the boxes are representing. Then, inside of these boxes, you are going to place arrows. Each arrow is going to represent an electron. Now, at this level in high school, you will not be responsible for drawing the boxes on your own. Obviously, you're drawing them today because you're copying what I'm giving you. But you'll see on your worksheet, on your test review, the boxes are there. You're just filling in the arrows. So we can talk tomorrow about how I would know how to draw the boxes, but that's not the concern right now. The concern right now is if I gave you boxes, do you know how to put the arrows in? Okay. So, while every box is an orbital, you'll notice that sometimes the boxes are touching and sometimes they are not. When they are touching each other, that means that they're equal energy and they are all part of the same sublevel. Because only orbitals that are part of the same sublevel would be same energy. So for example, when I have this little box by itself, that's what I would see anytime I'm talking about an S sublevel, because S sublevels only have a single sphere. One sphere, one orbital, one box. But if I have 3 boxes touching each other, that's a P sublevel, because remember the P sublevels had 3 dumbbells. And the reason why they are touching each other is because they are equal energy. This is going to mean Aufbau's rule isn't going to help us when we have to start putting arrows in these boxes, because if they're all equal energy, Aufbau says, well, we got to fill lower energy, and that doesn't help us here when they're all the same. So, lastly here, 3 boxes touching each other, that would represent a D sublevel. So it could be 3D, 4D, 5D. I don't have the coefficient in front, but it's 5 orbitals. Remember the 4 clover leaves in the dumbbell with the donut? That's a D sublevel, and again, they're all touching because they are equal in energy. But when they're not touching, they're not the same energy. So, the other thing is when you're given these boxes, they are already put in order for you by energy, with the lowest energies starting first, and then proceeding with higher energies as you move to the right. Reading from left to right, you're going from lower to higher energy. So I know we're going to fill these in a second, but that means 1s is lower energy than 2s, 2s is lower energy than 2p, 2p is lower energy than 3s, which is lower energy than 3p. They're already in order for you by energy. For space on my paper, I've done my diagrams from left to right, but you should be aware that they can also be done vertically. I can flip it vertically, and in that case, the lower energy sublevels, like 1s, would be at the bottom, and then the higher energy sublevels would move towards the top. So you're going to see that on your worksheet tomorrow. You're going to see an orbital notation where it's vertical, low energy at the bottom, high energy at top. All right, so what we're going to do is we are going to fill in these orbital diagrams using Aufbau, Pauli, and Hunt. Those 3 rules, principles, whatever, that we wrote down at the end of class yesterday. So listen up, because I'm going to explain why I'm making the choices that I'm making for where I put things. And then on the last one, I'm going to show you how I could mess things up, and you're going to try to tell me, well, whose rule did I mess up? Whose principle? Okay. So here we go. For example 1. We are going to do the orbital diagram for lithium. The first thing that I need to do is I'm going to need a periodic table so that I can go and figure out how many electrons lithium has. So here's my periodic table. Here is lithium. How does looking up lithium on the periodic table help me know how many electrons it has? What on there helps me with the electrons? The atomic number. The atomic number, remember, it is equal to the number of protons, but in neutral atoms, it's also equal to the number of electrons. So I know that lithium has 3 electrons total. Okay, so heading back to my notes here, that means when I'm done, I need to have a diagram that has 3 arrows for those 3 electrons. So now my job is, well, where do I put them? So here we go. Aufbau, Hunt, and Pauli are going to help us out. Aufbau, oh wait, one more thing. Guys, you know arrows, they normally have like a double head. For simplicity, we sometimes just do it with half the arrowhead. So if you ever see this, these are, a full arrow or a half arrow. Both are accepted for arrows. Okay? Either one's fine. All right, so here we go. Lithium, 3 arrows. Aufbau. Aufbau starts me out because Aufbau says I have to start with the lowest energies first, right? Lowest energy sublevels first. So those are always going to be furthest to the left or furthest to the bottom. I don't want to start with the 2s because that's higher energy. I need to start at the 1s. So that means my first arrow is going in the 1s box. Now, why did I start with an up arrow? That is just convention. We start with up arrows because that's the way that we do it. No other specific reason for that. All right, for my second arrow, Aufbau also tells me not only do I have to start with lowest energy sublevels, but I have to fill the lower energy sublevels before I move to a higher one. So if this is an orbital, how many arrows can I get into one orbital? 2. So guess what? I haven't filled this. So not only does Aufbau tell me I have to start at the 1s box, the lowest energy sublevel, but it also says I have to fill the 1s sublevel before I can even go to the 2s. So that's why my second arrow is going to go in the same box. But Pauli's exclusion principle is going to tell me something about that second electron that's going in the same box. Pauli's exclusion principle, you can't have 2 identical electrons, and so what that meant for us practically is if they were in the same orbital, they had to have opposite spin. So how do I make it look like it has opposite spin? Well, this second arrow, I'm going to point it down, not up. So again, Aufbau said I had to start at 1s. Aufbau says I have to fill the 1s before I can go to 2s. Pauli says they have to have opposite spin when they're in the same orbital. Okay, everybody with me so far? So that's 2 arrows down, 1 to go. Now that the 1s sublevel is filled, now I'm free to move on to the 2s, the higher energy sublevel. And again, just convention, we start with the up arrow first. And that's it, we are done. Right? Nothing else, no other arrows. That is the orbital diagram for lithium. 2 electrons are in the 1s sublevel, 1 electron is in the 2s sublevel, and these 1s electrons have opposite spin. All right, so let's do another example. We're going to do carbon. All right, let's do carbon. So I'm going to go to a periodic table, which you will absolutely have on this test. Here's carbon, and so that tells me carbon has 6 electrons. Atomic number 6, proton 6, electron 6. So when I'm done, I'm going to need 6 arrows in my picture. So once again, Aufbau says I have to start at the lowest energy sublevels first, and which one is the lowest energy, 1s, 2s, or 2p? 1s, the furthest to the left or the closest to the bottom. Aufbau also says I have to fill that 1s sublevel before I move to the 2s, because those are different energies. But Pauli says, hey, if you're going to put a second electron in the same box, it better have opposite spin. So now Aufbau is going to let me go to the 2s for my third electron. But I can't jump to the 2p, because Aufbau also says I got to fill the 2s, which is lower energy, before I move to the 2p, which is higher energy. That's why they're not touching. And then, since I'm going to put another one in the same box, Pauli says, wait, opposite spins though. So there goes my fourth arrow. All right, Hund's rule takes over when we get to this situation. Remember, these are equal energy. So even though I have two more arrows to place, I don't have to worry about Aufbau saying, well, I got to fill this box before I move to this one, because, guys, they're all the same energy. When they're touching, they're all the same energy. So this is when Hund's rule kicks in. And Hund's rule says, guys, spread them out. Put one in each before you put a second one. So I don't want to put those two arrows together in the same box. I want to put them in two different boxes. So here's my fifth electron and my sixth electron in two different boxes. So, questions. First thing, yes, we always put up arrows first. That is a thing that they all start with the same spin. So we should all have the up arrows first. I can't just make this one an up and this one a down. Next thing, some students are like, Mrs. Tate, can I just skip this box and put the sixth one over here? No, guys, this is just on a piece of paper. It's not like that third box is physically any further away in real life. So we don't need to actually, on the paper, make them further apart. We just need them in different boxes to indicate that they would be in different orbitals. Right? So keep them all pointed up for the first one, and just go ahead, keep filling the boxes one by one. All right, so that was Hund's rule. Spread them out before you double up. We didn't have enough electrons to double up, so that was a non-issue. Okay, so here we go. On this last one here, I'm going to start doing things wrong, so you might want to wait with your writing until I get more to being done, because I'm going to keep asking you what I did wrong for each part. So we're going to do sulfur. Go into a periodic table, sulfur right here, it's atomic number 16. Okay. So 16 electrons, 16 arrows when I'm done. All right, so here we go. I'm messing up. Don't write stuff down yet. Whose rule did I mess up? What do you got? Emma. Whose rule? Sophia. Aufbau. Why is it wrong?
Because you filled up the higher, you didn't fill up the lowest energy level.
Correct. I jumped to a higher energy sublevel before doing the lower energy sublevel. Okay. Whose rule is that a violation of? Who's that? Julia. Paul. Not Polly. Who's that one?
Is that still Aufbau?
Still Aufbau. Why?
Because you didn't completely fill one else.
Yeah, I got to completely fill this. It's not just enough to start there, but I have to completely fill it before I can move to the 2s, which I haven't done yet. Okay, so that was a violation of Aufbau. Who's that a violation of? Julia. Polly, because now I've got two arrows in the same box, pointed the same direction. Not cool. They got to have opposite spins. So let me fix that one. Who am I violating there? Aufbau because?
You get to fill it.
Got to fill which one?
The 2s.
Got to fill the 2s before I can go to the 2p. Who's that a violation of? Polly because? They don't have opposite spin. Who's that a violation of? Emma. Not Aufbau. What do you got, Zach? That's a Hund's violation. That's Hund's rule. Hund's rule says When these guys are touching, we don't double them up until everybody has one. So here we do need to spread them out. So it should have gone, this would have been my 5th, 6th, and 7th. Who's that a violation of? Alpha. Why? Guys, I haven't filled the 2P. I put one in each, but it's still not full. Each box can have 2 arrows. So that's a violation of alpha. So that's why when I go to that, what was that, 7, that 8th electron, I got to circle back. Now I can put in a second one here, a second one here, a second one there. So you guys see how it spread it out before I cycle back to put in the second one? All right, so then what? That's 10 electrons right there. So I've got 6 more. I'm going to kind of move that along. So there's 11, 12, and now I have 4 left. Who's that a violation of? That's Hund's rule. That's not Hund's rule, right? I can't double them up until I put one in every equal energy orbital. You have to spread them out. Everything has to have one before it can get a second. So what that means really is I just got to take and spread these 2 out. So that would be your last 4 electrons. Okay, and so just depending on how many electrons you have, you don't always fill up that last sublevel. But everything before it should be filled. Just the last one may or may not be filled depending on how many electrons total are available. Now, I didn't draw them on here because we're not going to do any with F sublevels, but how many boxes would I stick together if I had an F sublevel?
Maybe 7.
7, right? 1, 3, 5, 7. Okay. All right, so remember, you guys don't have to know how to draw the boxes yourself. You would just have to be able to pick the arrows in if I gave you the boxes. So if that's what you're confused about, it's just about the arrows, not about the creation of the boxes. Okay. So what we're going to move on to now is another way to describe the arrangement of electrons, but it's going to be more text-based, more textual, not pictures. And it's called electron configuration. In electron configuration, you're going to string together a series of blocks. Each block has certain information, and your electron configuration could have anywhere from 1 block to 10 blocks, just depending on how big your element is and how many electrons you have to describe. Every block will consist of a coefficient, a letter, and an exponent. And if your exponent is the number 1, you have to write it. So we will be writing 1s as exponents in electron configuration. All of this information, what does it tell you? The number 2 tells you the energy level that the electron is at. In this example, the letter P tells you the orbital type, S, P, D, and F, that the electron is in. And then the exponent 3 in this case is telling you how many electrons are in that energy level's orbital type. And guys, I separated this out, but remember the 2p together, that's actually the name of the sublevel. This is the 2p sublevel. Remember how sublevel names can also tell you the energy level that you're on?
Oh, when we write the P, does that have to be like smaller than the T?
I mean, it's a lowercase p, yes. Yeah. I mean, I made it big here, but you'll just be doing it on a regular line. Like, you don't have to make it giant. So I'm going to start first by showing you how I could get electron configurations from orbital diagrams. Because in your orbital diagrams, they've already told you all of your sublevels down here. And then once you fill it in, you know how many electrons are in each sublevel because you can count the arrows. So if I were to write the electron configuration for lithium, I would write 1s, because that's my first sublevel. And then how many arrows were in that box? 2. I put an exponent 2. And then here, this was the sublevel 2s. And how many arrows were in that box?
1.
Just 1, and we have to write the 1. Hey, guess what? That's the electron configuration for lithium. And we read that 1s2, 2s1. We don't say squared or cubed. We just literally read the numbers. That's 1s2, 2s1. So if I were to do this for carbon, I would start off with the 1s sublevel, 2 arrows. Then I would go to the 2s sublevel, which also has 2 arrows. And then here I go to the 2p sublevel, and guys, I just counted up. There's 2 arrows. So in some ways, electron configuration doesn't convey quite as much information as the orbital diagram, but it gets the job done. So you guys try to write for sulfur. Write out the configuration from the orbital notation. So what you should have had is 1s2, 2s2, 2p6, 3s2, 3p4. So it's 2 different ways to express very similar information about the location of every electron in an atom. Now, you're not always going to have the orbital diagram first. There's going to be, most of the time they just say, hey, write the electron configuration for, and give you an element, and you don't have boxes or anything. So how are you going to do that? We're going to use the periodic table to help us. So like these were given to you in that order. How did you know to do that? We're going to show, or you're going to see now how we can use the periodic table to figure out that order. So with that, we need to make a sketch of a periodic table. Listen to how I'm explaining that you can do this, and then try to replicate. We are taking our periodic table and we are breaking it up into 4 rectangles. This first skinny rectangle right here should be 7 lines tall. Okay, so make a skinny rectangle that's 7 lines tall over here. Then this middle rectangle, notice it's only going to go from the 4th to the 7th line. And if you'd like to number your rows here, go ahead and number those out. 1, 2, 3, 4, 5, 6, 7.
How much is going to be on the bottom?
It's only 2. Yeah. Okay. So this rectangle in the middle is only the 4th to the 7th row. And then this rectangle over here to the right is from the 2nd row down to the 7th. I don't really care so much about how wide they are, but the heights are important. And then just down here, this is just another long skinny rectangle, and it's only 2 lines tall. Okay. So just give you a second there to try to get that down. Let me erase some of that. So what we've done in this image, in this drawing, is we've taken our regular good old-fashioned periodic table and we have split it up into 4 blocks. That's what we call them, blocks. Let me just show you on the real periodic table where the separations were, because they're not separated on the real periodic table. They're all stuck together. So if I were going to draw this out, this was your tall skinny rectangle. That would have been the first 2 columns. That was one of your blocks. Then this was that long middle rectangle. That was a second block. Here, this was the other one to the right that was a little taller but not quite as tall. That's a 3rd block. And then down here, this is the 4th block. Now, a couple of things. You're like, what about helium up here? When it comes to doing electron configurations, helium should be over here on the periodic table. You don't need to move it on yours, but we ignore it in this spot. It actually fits in this spot with how many electrons it has. There's a reason it's over there that we'll get to next unit, but for electrons, it would fit there better. Each one of these blocks corresponds to different orbital types. So that's what we're going to label in our notes here, is that this first skinny block over here, this is your S block. In the middle, this is your D block. On the right, this is your P block. And down at the bottom, this is your F block. In addition to that, we're going to be able to use the row numbers over here to even say exactly which sublevel it is based on the energy level. So when it comes to the S and the P block, the energy level will correspond directly to whatever row you're on. Meaning that hydrogen and helium, those elements we would say are in the 1S sublevel because you're on the first row and you're in the S block. And then here, this would be lithium and beryllium. Lithium and beryllium are sitting in the 2S sublevel, second row S block. And then sodium and magnesium on that third row, they're sitting in the 3S sublevel, third row S block. Moving down, fourth row S block, fifth row S block, sixth row S block. For the S block, the row number corresponds to the energy level. And then when you're in the S block, that's the orbital type that you'll have. The same thing will follow in the P block. You just might have to stretch over here because remember your P block actually started on the second row, not the first row. But boron starts the P block. And then aluminum, well, boron starts the 2P sublevel. Aluminum starts the 3P sublevel. Gallium starts the 4P sublevel. Indium starts the 5P sublevel. Thallium starts the 6P, and I don't remember, it's one of the 113 man-made ones, starts the 7P. So now, why did I skip over the D block? Well, that's because, remember how I told you that we have to do things in order by energy, and sometimes they go in an order we would not expect. Well, we're going to fix that right now. When you get to the D block, instead of saying this is the 4D sublevel, you are going to subtract 1 from the row number. Meaning, if I'm on the fourth row with scandium, I'm not going to write 40. I'm going to subtract 1 from that row number, and that means scandium starts the 3D sublevel. And then yttrium is right here in the D block. But I'm not going to say yttrium starts the 5D. I'm going to subtract 1 from 5. Yttrium starts the 4D sublevel. And then lanthanum starts the 5D. Actinium starts the 6D. Why are we doing this? It's just because it's going to help us put things in order by energy. Help us put them in sublevel order by energy. All right, so last, let's check out this F block. Guys, the placement of the F block was strictly just trying to make life easier for printing on a piece of paper because the F block doesn't really just go down there. So I'd like to show you where the F block really is supposed to be on a periodic table. So here's good old-fashioned periodic table here, ptable.com, best periodic table. This is where the F block is supposed to go. If you actually look at the atomic numbers from lanthanum, La, to hafnium, Hf, it jumps from 57 to 72 because all of that stuff at the bottom is supposed to go in the middle there. But this would be much more difficult to print on a piece of paper. Right? Because it would be long and skinny and tiny to fit it. I can barely see it on my screen. So first thing, the F block goes between which other two blocks? S and D. It's between the S and the D block. And then what rows does the F block correspond to? 6 and 7. So it should be on the 6th and 7th row between the S and the D block. That's your F block. All right, so let's pull that back. So that's why I put these stars here, because this is where your F block would have been inserted. So once again, to get things in order by energy, for the F block, what we're going to do here is we are going to subtract 2 from the row number. Meaning, even though I'm on the 6th row here, that's not starting the 6F. It's not even starting the 5F. It's starting the 4F sublevel. And then this is on the 7th row, but those elements, they're in the 5F sublevel. So by knowing this information, by being able to look at anywhere in the periodic table and say, hey, this element's in the 4p sublevel. Hey, this element's in the 5s sublevel. Hey, this element's in the 3d. If we can do that identification, then we can read this table from left to right, top to bottom, and all of our sublevels would be in energy order. Because it would go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, right? They're all in order reading from left to right, top to bottom. That's why we didn't have to memorize the order. We just have to know about the subtraction for the D's in the F block. That's it. All right, so now that we know this, we're ready to write some electron configurations. So we're going to be doing a bunch of examples. I've got them all listed out here. I'm going to write most of them on my periodic table, though, and then you guys are going to just copy it down with me. So here we go. On my periodic table, I'm going to erase my block colors because I got to write some other stuff. You will always begin up here at hydrogen. And your rule is that you have to read from left to right, top to bottom, listing every sublevel that you would be passing through and counting how many electrons you would be adding until you get to the element that you're trying to write the configuration for. So for example 4 in your notes, if you guys want to write down, we're going to write the configuration for lithium. Okay? All right, so I have to start at my start point. That's up here at the beginning. And what I'm going to do is I'm going to focus just on this top row. And on this top row, I'm like, all right, this is a sublevel. That's one of my blocks. What sublevel is that? I'm on the first row. I'm in the S block, so that is the 1s sublevel. Then I need to figure out how many electrons can fill that sublevel. You count your elements because every time we move from one element to the next, we're just adding one electron. So hydrogen had 1 electron. When I move over to helium, that's 2 electrons. And then that's it. That's the whole sublevel. So 2 electrons would fill that sublevel. And again, you're just counting your elements. Some students start to mix this up with the orbital notations and the arrows. Nope, this is not the same thing. Just each element has 1 more electron than the previous. So every element is 1 more electron. All right, and then if I go along here, guys, there's nothing else on the first row. The first row is done. So now I'm going to move down to the second row. And on the second row, the first sublevel, reading from left to right, is going to be right here. And I name it. Second row, S block. That is the 2s sublevel. And then now the element I'm trying to write the configuration for is also in that sublevel. So the rule is you just count till you get to that element. Lithium is the first one. That's it. There's just 1 electron there. If I put S2, then that meant I would have made beryllium because beryllium is the second one. And guys, when you're done adding up these exponents, that should equal your number of electrons in your element. Because lithium had 3. So that's a kind of after the fact thing that you can do to check. But guys, this is your answer to example 4, 1s2, 2s1 for lithium. So make sure you wrote down lithium on your paper and make sure you wrote down that configuration. Hey, guess what? Whoopsie, went the wrong way. You guys did this up here too. Oh look, 1s2, 2s1. You did it with the orbital notation, but now I showed you how to do it with the periodic table and no orbital notation. So again, make sure lithium, 1s2, 2s1. All right, so let's move to carbon. Let's do carbon. Let me clear out and reset this for another example. Okay. All right, so I like to just go kind of mark off carbon. That's where we're getting to. So here we go. We started hydrogen. We got to go left to right, top to bottom until we get to carbon. So starting off here, that's the only thing on our first row. What sublevel is that? First row, S block. That's the 1s sublevel. And it takes 1, 2 electrons to fill it. because helium has 2 electrons. Guys, if I stopped right there, that's the configuration for helium. If I stop anytime early, I'm just making a different element. That's the whole point, is you just got to get to your element. All right, move to the next row. This is the first sublevel on the second row. That sublevel is the 2s sublevel, second row s block, and it takes 1, 2 electrons to fill it. But keep going, guys. There's more stuff on the second row. This is also on the second row. Yay. Sorry. Take my stuff away. So that sublevel, once again, second row, but now we're over in the P block. That's the 2p sublevel. And this is the sublevel that my element is in. I just need to count till I get to it. 1, 2. 2p2. Carbon's the second element in the P block. That would be 2p2. That's it. That's our configuration for carbon. And guess what? That was example 2 in our orbital notation as well. But now we're doing it with the periodic table, not with orbital diagrams. So I'm doing a lot more examples, but pausing right here. Questions right now on what I'm doing. Okay, then let me reset for the next one. All right, next example, 1s2, go away. I don't like my stuff. All right, my next example is going to be not sulfur. We're going to switch it up to sodium. Sodium, Na. Here we go. Sodium right here. So we have to start off with hydrogen. That is the first sublevel on the first row, which is the 1s sublevel. Guys, this gets repetitive. We always start at 1s. And a 1s always takes 2 electrons to fill it. Guys, that's true for every s sublevel. Always would take 2 electrons. Nothing else is on the first row, so I move to the second row. There's my next sublevel in my second row. That is which sublevel? 2s, second row s block. And how many electrons fill it? 2. All right, and then I move to the 3s, right? No, because I'm not done with the second row. Make sure that second and third row, you keep going. There's stuff over there on the right side. What sublevel is that? That's 2p, second row p block. And how many electrons to fill it? Well, let's count. 1, 2, 3, 4, 5, 6. 2p6. If I stop there, I just made neon. But I don't want to make neon, so I got to keep going. All right, so then we finally get to go to the third row, and this is the first sublevel in the third row. What sublevel is that? 3s. And then how many electrons to get to sodium? Just 1. If I wanted to make magnesium, then I would have said 3s too, but I don't.
How do you get 6? I thought you could only have like 3 energies.
So remember, this is a whole dumbbell, 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 and they each have 2. So remember, there's an electron here, 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 here. It's an entire sublevel, right? It's a whole sublevel. So remember, an S sublevel could have 2, a P could have 6, a D could have 10, and an F could have 14. All right. Other questions? Okay, so that's your answer for the sodium example. Resetting for another one. Okay, here we go. Next one is going to be, I'm not going to write that down. You guys have it. Vanadium. Vanadium, V. Okay. All right, here we go. Vanadium is right here. Start at the beginning. What should I write for that whole first row? 1s2, guys. If your first row is filled, it's always 1s2. All right, let's kind of put this together. Guys, this is my second row, and I know it's filled. So what can I write for the second row? 2s2 and 2p6. A filled second row is always 2s2, 2p6. All right, even though we haven't done it yet, the third row, if it's filled, is going to look very similar to the second row. Because if the third row is filled, I'm going to write 3s2 and 3p6. This is your 3p6. Okay, so now things are going to get trickier. So remember, on the periodic tables you guys get to use, they don't separate the blocks. So don't forget, this is your separation between those two blocks, and this is your separation between these two blocks. It's where they changed heights. That's where they split. That's going to be important because that means this is the next sublevel. And what sublevel is that? That's 4s. And how many electrons? 2. And so that makes this the next sublevel, which is what? Is it? 3D. Good job, guys. Yay. It's not 4D. That's going to be the one on the multiple choice that you guys would go for. It's not 4D, it's 3D. Remember, with the D block, you always subtract one from the row. So this is going to be 3D. Let's put that in pen, not highlighter. And then just like before, I still count till I get to my element. 1, 2, 3. 3D3. How we feeling? Okay, let me give you one more for today, and I want you guys to try to write it out a little bit on your own first before I jump in. So, low stakes right now with notes. You guys, for example, 8, I'd like you to do arsenic AS. Arsenic AS. I will put my table back up on the board. Arsenic AS. And that is arsenic over here. Okay, so let me give you a second, see what you can write out for arsenic. All right, check in with the neighbor next to you real quick. See if you guys came up with the same thing. It got quiet. I'm putting up the answer if you guys had any discrepancies, but let me get to it here. So here's the fourth row, 4s2, which would be followed by this right here would be 3d10. It's 10 if you count it. And then you would end with over here would be what? It goes back to 4p, and then it would be 4p3 because arsenic's the third one over. Okay. So we'll start out with an even trickier one tomorrow, and then we'll talk about shortcuts and exceptions. Okay. But that's our basics for configuration.